Welcome to the second day of Kopernik Forum 2026 Frontiers in Interdisciplinary Mathematics. We will continue with academic sessions. This block will be chaired by Professor Wang Xiaoping from Chinese University of Hong Kong, Shenzhen. Professor Wang, please.
Okay. Thank you. Okay. So this morning we have two sessions. The first session is towards trustworthy AI, okay, physics and verification. Okay, I'm honored to introduce the first speaker, Professor Raymond Chen from Lingnan University. I know Raymond very well. Raymond got his PhD from Koran Institute in '85, and same as me. And he has been worked in different universities in Hong Kong. Started with Hong Kong U and HKUST and Chinese U and City U, and he was the Dean of Science at City U. And now he's vice president at the Lingnan University. Raymond has done many great works in applied math and scientific computing. Okay, today he's going to share some his thoughts on the AI, and the title of his talk is P-Local Net Physics-Informed Neural Network on 3D localization with rotating point spread functions. Okay, Raymond.
Oh, this one. Okay. Okay. Thank you. So how do I move this? Oh, there. Okay. Thank you. Okay. Let me try this. Okay. Good. Okay, thank you, Xiaoping. I know Xiaoping also for more than 20 years, I think. Yeah. Today I'm going to talk about this. So the title seems long, and there may be some words that you don't understand. So I will try to explain them one by one later on. So let me start with this is the outline of my talk. So I will go through them one by one. So first, let me mention the problem. So the problem is that so we are trying to locate the 3D locations of points using, for example, a microscope. So if you want to locate the 3D locations, that means X, Y, and Z. Z is the depth. Okay. So then, how do you do it in a microscope, for example? So then you have to take different images. Okay, so so for example, at the first time frame, time step, so you take one image, and then you get well, basically you rotate the depth or the focus of the microscope, and then at each time step you take one image. Because you know the focal plane, then you can decide the depth of this image, and then you can determine the Z location of the points. Okay, so and then by combining all this, I don't know what doesn't work. Is it? Doesn't work. Our battery. But I don't. Oh, can you go back? Oh, let me try that again. No, that's not. So maybe I go on with this slide. So then at different time step, you take one image. So, okay, hopefully. Now it works. Okay, thank you. Okay, this is okay. So at different time step, you take an image with different depth and then now by combining all this, then you get the 3D locations of all the points. Now, of course, if you do this, then you take a long time, right, to get the 3D location of all the points. Now, why do we have to do this? Because, well, if a point is at the origin, exactly on the focal plane, well, then you see that the image should look like this. But then if the point is above the focal plane or below the focal plane at the same distance, then they have the same image on the imaging plane. So that's why you cannot decide the depth of the point. So that's why you have to take a lot of images at different depth to decide the location of all the points. Okay, so that's the problem. Okay, now what are we trying to do? So we are trying to get the 3D locations by not focusing the points on the focal plane, but by defocusing. Now, what do we mean by this? So instead of taking many images, our idea is that we put a particular lens into the microscope, and then we will take only one picture, not many pictures. One picture. And then with this one picture, something like that, and then we do an inverse problem. And then by solving the inverse problem, then we get the 3D locations of all the points. Now, if we can do that, then we save a lot of time, right? So we don't have to take a lot of images. Now, why can we do that? It's all because of the lens, the particular lens we put inside the microscope. Now, this lens is developed by one of our collaborators. So basically, if you have a point that is on the focal plane at the origin, now what you see on the imaging plane is something like that. It's no longer on the origin, and then it has some ring on this. Now, and then the nice thing is that, so if a point is above the focal plane or below the focal plane, then the images that you see are different. You can see that. So by looking at the rotation, then you can determine the depth of the points. So that's why by solving this inverse problem, then we can determine the 3D location of all the points. So that's the idea. Now, why do we have to determine the 3D locations of all the points? Now, this is, well, basically, one of the most important applications is single molecule localization microscopy. So the idea is that, so basically, we try to go under the limit of the optical light. So, for example, if you use an optical light to look at some structure, then you, if the structure is very small, then you see only this. But then by allowing the structure with points that shining at different time step, then then you take different images, and then finally by combining all these images with points, then you get something like that. Okay, so so this is actually invented by this professor and then he got the Nobel Prize in chemistry in 2014. So the idea is that if you see something like that you don't see anything, but then by locating the points each time, at each time step you locate the this is the 2D picture, not a 3D even. So by locating the points at different time steps finally, and then when you combine them together, then you can see a very clear picture of this 2D image. You can even see the points, the numbers. Okay, so that's the whole idea. Okay, so this is an image where if you do not if you use an ordinary microscope, then you see something like that. But then if you use this idea by locating the points and then combining them together, then you can see something like that. Okay, so that's very important to go beyond the optical limit. Of course, well, by doing this, even for one 2D picture, you need a lot of time. You need a lot of images in order to do this. You think about that. If you want to look at the 3D structure, then it's even worse, right? So another application that we are also very interested in is to locate the space debris. Now the space debris, even if it's very small, if it hit a spacecraft, then it can even break the window, the glass. Okay, so then we have to decide, okay, where they are. So this is a 3D location, right? Point locations. But then we want to take a 2D image and decide the 3D location of all the space debris. Okay, so this is the problem setting. So now then, in order to solve the inverse problem, so first I have to tell you the forward problem. Then from the forward problem, then we can invent a method to solve the inverse problem. So this is the forward problem. So suppose I have a pawn. Do we have a? Oh yeah, that's good. Suppose I have a pawn at the xy origin. Okay, this is at the origin, but then it's the delta c distance from the focal plane, And then so what is the image? So this is the imaging plane. So the imaging plane, if you consider any point S on the imaging plane, so what is the intensity of this image? So this is given by this formula. Okay, so for any S on the imaging plane, so basically you integrate this and then you will get the intensity on this imaging plane. Now you look at this, there is a theta here. The theta actually incorporate the distance or this depth here. Okay, the delta c is the depth. So the depth affect what you see on the imaging plane. Okay, so that's the forward problem. Now with the forward problem, then now this is when the point is at the origin xy equal to 0. Now suppose you have a point that is not at the xy equal to 0, then what happened? Then basically we can just do a convolution. So you look at this image where the point is at the origin, and then you just convolve with it with a delta function, and then also we assume that the points they are not of uniform intensity. So if the intensity f1, or the f1 basically measure the number of photons, then you multiply by f1. So this is what you will see when a point have f1 intensity and x1, y1 location, and that is what you see. It's given by this formula. Now if you have another point at another location, okay, with another intensity, then you just add them. Okay, so if you have many points, okay, then basically you just sum them together with this formula. And then of course when we observe the images, you always have noise, so we also have a noise. So this is the forward problem. Okay, so now what I just mentioned to you is what happened in the continuous space. But then usually when we compute that, we discretize that into a grid. Okay, and then this is what will happen. So basically, so you have a point in the XYZ location. What it is doing is basically convolve this point with a 3D convolution operator, and then you take the last slide of this is what you observe here. So basically that's how we discretize this. Okay, or if you have 2 points, let me show you. If you have 2 points, sorry, here. So basically you convolve it with this 3D convolution operator, and then you get something like that. And then you take the last slide out of it. Then that will be what you should observe on the imaging plane. And then of course, as I mentioned before, so then you add some noise. That should be what you observe if you are doing simulation. Okay, so this is the forward problem. So if you have a point here, 2 points here, then this is what you observe. Okay, and then of course in the old days, then how do we get from here back to here? So we use a variational approach to get from here to here. So let me mention to you what is the variational approach. So basically, maybe I go back to emphasize the location, the notations. So the notation is G is what you observe on the imaging plane with some noise, and then we want to get back here. T is the operator that take the last slide of the cube. Okay, so which get you this. So these are notation. Okay, so in the old days, you would do something like that, right? So with the observed image, you try to find a next such that after the convolution, after taking the last slide, it will be close to what you observed. This is what we call the data fitting term. And then because X is points, so you want to have some kind of norm to specify the sparsity. So some kind of sparsity promoting norm. So for example, for the Poisson noise, then you will use the KL distance. between these two, the observed image and the one that you want to find, and then with some zero norm to emphasize the sparsity in the solution x, right? So because the x are points. So this is in the old days. So what you will solve this problem with? Okay, so let me just mention. So for Poisson noise, so the KL distance is defined like this. So that means you will have to solve something like that. Okay, so B here is the background noise, and then X is the solution. Okay, so you in the old day you will solve this problem with some optimization technique. So this is called the KL and L0 problem. But then, the L0 is difficult to solve. Actually, so then usually if you really want to solve it using optimization algorithm, then you have to approximate by some other thing that can be compute. Okay, so then here in the old days we approximate the zero norm by this one. So here I illustrate that actually this norm it approaches the zero norm, which is this one. Okay, when the a is going to 0. Okay. So that's why we paste the zero norm with this. So this is the KL with this approximation of zero norm. And then how do we solve it? If you are using an optimization problem to solve it, then basically you use the iterative refinement with L1, and then use ADMM, alternating direction method with multipliers. Okay, so this is the old trick. And then let me show you. Also, one more trick is that so if you solve it using this optimization problem or other problem actually, so then you will get some kind of points that are very close together. But then so these are usually the because of the algorithm. Then usually we have to gather them into one. If they are so close, then we gather them into one pixel. So if they are 2 pixels apart, then we gather them as one point source. Okay, so this is what we call the post-processing. Okay, so then we try different example with different point source, and also different distribution, and also different. This one is with 2,000 photons. Then we try that. And then this is the result. So let me show you. So this is the observed image. I think this is a 15 point source. With it is observed image. And then this is the denoised image with also the points here are the XY location of the points. We find. And then if you look at the 3D locations, we can also determine the 3D location. So here is that the circle are the ground truth of the points, and then the plus is what we compute and for the XYZ location of the points. So you see that for 15 points, we have a very good algorithm. But then if you look at the number of points when it increased, then for our method, basically the precision, the recall rate is very good. So that means we basically can identify most of here, for example, we can identify 95% of the true point source. But then the problem for this optimization algorithm is that when the point source are when there are a lot of point source in the image, so then we have many false positive. We have many false positive. So then we have to improve on the algorithm. So before I tell you using the neural network to solve it, so let me tell you one of the applications that we have tried before. So here we put this is also simulation. I should emphasize using real data. So here we assume that we have this lens into the telescope. This one is a telescope. We put it, and then we obtain some data. Okay, and then we try to locate the 3D location of the space debris. Now, but here we also one thing I should emphasize is that in fact for the forward problem, you can see the lambda here. Lambda is the wavelength of the light that you use to gather to collect the image. So that means if the lambda change, the image will also change. So here then we use this example from NASA. Okay, so here we have 5 different light frequency to get the 15-point source at the same location, but with different light source. So you see that with different lambda, then the image are different. Okay, but then basically they are the same 15-point source. But why do we want to take 5 images with different wavelength? It's because we not only want to determine the 3D location of the points, but we also want to determine the material of the points. This is what we call the hyperspectral imaging. Okay, so we have 5 frequency. With this, we should be able to determine classify the material. So let me show you the results. So this is these are the 5 different material with corresponding to different frequency. Okay, so now we try to determine not only the point source location, but also the material. So you see that so here circle is the 3D location of the points, and then the star are our estimated location, and the color represent the material. So you see that we can basically determine all the locations of the 15 points, 3D location of the 15 points, and and then for 14 points we can decide their material, except for this point. So this point we can determine its point location, but we fail to determine the materials, so it misclassified. But in any case, so this is a good result. Okay. So now I tell you that. So how do we improve on this using neural network? Okay. So using neural network, the problem it actually become easier, right? Because well, we know the forward problem. So now then we can generate many training data, right? So because we know the physical laws, given the points, we know the law. So the integration that get this. Okay. So then with this, then we can easily generate many training data and to train our neural network. And then with the neural network, then if we are given this image, then we can use the neural network to determine the points. Okay, so basically that's the idea, right? So we know the point spec function, the 3D, so rotating PSF from the physical law. Okay, and then we generate many point source, and then we convolve it, and then we get some images like this. We take the last frame. Okay, after we do the convolution, we take the last frame, then we get this, and then we add some noise. And then we change our neural network such that it will give us back this. Okay, so that's the whole idea. And then when we train this, we also put some points that are the XY location are the same, but then the Z location are different. So that when we train the neural network, then we should get something good. Okay, so this is the whole idea. And then when we test it, of course, now then when we test it, then basically we test it also using some very tricky example. For example, this one we test it with some points that are basically vertically the same, but then spatially vertically are different, but spatially are the same. So that then we try to see whether the neural network can separate them. Okay, so we try many like this. Okay, so this is a neural network, a very standard neural network. Okay, so now but here in order to improve on this, we actually use the forward problem in our neural network. So that we become what we call the physics-informed neural network. So the whole idea is that the neural network's loss functions will consist of this this term. This is the KL distant term, and then the approximation of the L0 norm, together with the standard. This is the most standard loss function for neural network, right? So this is the root mean square error. So instead of just a root mean square error, we add the variational, the forward problem into our loss function, and then hopefully then with this then we can improve on that. So this is the whole idea. So let me show you. Okay, so this is how many point source? 30 point source. So So we try this example with Poisson noise. Now this is the variational approach. You see that most of the point sources we can identify them correctly. But the problem with variational approach is that there are many false positives. So you can see the false positive by the triangle here. Okay, so it generates many false positives. Now if you use the neural network with only the standard loss function, that means the root mean square. Okay, if you just use this loss function, then this one. Now this one, well, you can see that it already an improvement over this. All the points are located correctly, but then still there are some false positive. But if you add the forward problem into the loss function, then actually now you see that basically there are no false positive. So we solve the problem correctly for 13 point source. So you see that by adding the forward problem into the loss function, we can improve on that. So you see now the result is much better. Okay, so even for 40 point source, okay. So finally, let me. So all these are simulation, and right now we are doing real data now. Because our US partner they finally generate this lens. Okay, this is the lens. Theoretically, it look like this. In practice, it look like this. Okay, so then you put it on top of the microscope. Okay, so put it here. Okay, and then you take the images. Now, then you see that, well, in theory, the image should be like this. Okay, on the imaging plane, on the focal plane, it should look like something like this. And then when it is above or below, then it should look like something like that. That's in theory. But in practice, after getting this lens, and then that's the image that we are getting. Okay, so it's kind of different. But in any case, so now we have real data. So you can see that. Okay, so this is an image where. Oh, sorry. This is an image, what we call the, I should say that, okay. So this is called the beads, okay, fluorescent beads. So basically, these are that are point source, fluorescent point source. We put it on exactly on the focal plane, then you will see something like that in the imaging plane, okay. But now when we move this plane up and down, okay, and then we take the video, then now you see that they are rotating. Now you see, okay, so when we move it up and down, so the image rotates. So the rotation tells you the depth. Okay, now with this data, now we have the data, real data. So we can use this real data to train our neural network. Okay, we use this to train our neural network now. Okay, so this is what after the training, then we get something like that. But as I mentioned before, we usually get something like that. But then for some of we have to do some processing. That means that if they are very close together, then we have to cluster them into one point. So this is what we have done after the processing. That you see that we still have one false positive here, but then basically the points are located correctly. This is with this is with real data, okay. And here is some DNA. I think DNA in using the microscope, and now we can actually compute how it moves in 3D space, okay, using just this kind of techniques, okay. Previously, then you have to take many pictures. But now for each picture, we can determine the 3D location immediately. Okay, so then we can check the DNA motion more accurately. Okay, so I have to have 1 minute. So let me conclude. So basically, what I've told you is that we have this rotating PSF that make 3D locations of points easily just from a 2D image. And we have tried the variational method before, but then it has many false positives. And of course, the straightforward idea is to solve the inverse problem using a neural network. So, for example, this is a neural network that we tried at the very beginning with the root mean square as the loss function. But you see that it still have many false positives. Finally, we enhance it by using the forward problem. We put the forward problem into the loss function, and then it get some good results. So so these are the reference. Actually, these are the reference. Oh, strange. Sorry. How come it's? Oh, sorry. But then you can look at my website. Okay. Thank you very much. Thank you.
All right. Thank you, Raymond, for a very nice talk. Let's see if there's any quick question.
Yeah, well, basically, we are doing this kind of small, very small, because, yeah, of course, I should say that, so we are doing cell images, not like organ. Yes, very small image, because we want to look at this, for example, DNA structure, things like that.
Oh, okay, good, thank you.
So you determine 3D positions from 2D image, right?
Yeah, from one 2D image.
Yeah. Is there a uniqueness issue?
Well, so because yeah, I guess you can always find some example where I understand.
Right.
So I think
Okay.
there is not unique, but then basically with this points the non-uniqueness, I think it should be small. Okay.
Yeah. So because the accuracy looks very very good. Yeah. All right. If no more questions, let's thank Rima again.
Okay. Thank you.
Thank you. Okay. The next speaker is Professor Hong Lee Trong. Okay, from Gosar University. Is that right?
No, it's Vietnam National University.
Okay. So Dr. Hong is a professor at the he received his PhD from Meiji University. Okay, he's actually a pure mathematician, I guess.
Yes.
Yeah, but now he's working on the AI-related topics, and he is actively developing frameworks that connects formal methods with data-driven computations, and aiming to enhance the reliability and transparency in AI-assisted mathematics and education. Okay, so today he's going to talk about formal verification of algorithms, bridging mathematical proofs, and reliable softwares. Okay, please. Okay, let's walk.
Okay, first of all, I thank organizer for giving me a chance to talk today. Today, talk about formal verification of mathematical proofs and software. This presentation so how we use formal methods to the same as lean prover and connect mathematics problem with software development. It's what is lean? Lean is a programming language and help the proving mathematics theory. Lean is run on something we call the choose kernel. It's the choose kernel is very small with 8009. With the kernel helps it helps it the proofs. You given the proof in the lean. You can export it and verify, double check that everywhere. And lean is very the extendable and flexible. We know that the lean is a development and mathematical develop the lean is committee and next is why we using the lean. Lean have the matlib. The matlib is library. The matlib is library generated by a community of mathematicians. Its inclusion more than 200,000 theorem and has been building by 715 contributors. It is not. It is the traditional math topic for basic algebra. So it's also adding cutting idea to research advanced the advanced research mathematics and now the matlibs become to the fundamental data set. We training the AI system for automatic reasoning. Yeah. This here we see that lean is not used in computer science. In lean used by the many better mathematicians. For example, we see that the 6 field model wins model active development the lean. For example, the tensor and Peterson. Tensor use equation use lean to study the equation theory projects and polymath. And Peterson used lean to formalize high the complex his result liquid tensor experience. Kevin Boozer, he is leading the project formalization related to Fermat last theorem and many major challenges in mathematics. You see that here. This here is a great story. In 2020, Peterson was nothing sleeping. He with his result. He don't know that his result is true or false, and he put a formalizer is and John Common leader this that the project is finished with some the small mistake, but the team don't understand full the proofs, but Lin says that is everything is true. Now we know that every AI system have a solution. International mathematics Olympiad problem use given the full proofs by use Lin. For example, the alpha proofs from Google DeepMind have got a sliver middle IMO. And Aristotle from harmonics got a gold medal last year. And this proof from Bidance gets a silver medal. IMO is 2025. They mark three team worked independent, but they choose on the link to base the proof. You check that the proof. Yeah. This here we see that the atom have the perfect 20 and 20. The Putman, the deep state, the proof is 18 more than the 18 9 in the minimal F4F database. Harmonics developed by the Aris AI gets a model, gold medal. Yeah. But this here is the critical point by the 10,000. The 10,000 sees that the every AI cheats everywhere, but cannot pass the small kernel. For example, in the NIN is have the small kernel, and that's the great sound, absolute sound. Yeah. Now I want to apply this here to study in the pure mathematics and symbolic algebra computation and Christopher. Yeah. Now I introduce what is the Calabi-Yau variety. The Calabi-Yau variety, this means is the smooth variety of dimension 3, and such that some condition here. And I don't go into details its definition, but we know that the X is a complex intersection in the Pn such that the condition here, for example, is in the P4, the hyperplane of degree 5 is Calabi-Yau. Yeah. But the question is how can the classification of Calabi-Yau 3/4 in the P6? We don't know how can the classify Calabi-Yau 3/4 in the P6. And but in the P7 we have this some lead is Calabi-Yau here, and in 2026 the group is has we only have the 11 family of Calabi-Yau 3/4 in the P7, but I using the lean and computation find this more than 3 family. Yeah. This how can the find I using to the deformation theory and algebra computer and NIN to find these 3 family. And now I go to this the last section. In the last section, I want to talk about in the elliptic curves. This curve is 25519. It's the curve here used in this curve is based on signal commuting. This this my group is verify the formula in here. How can verify function correctness? This elliptic curve is in the rush. Now the first step we change the function in the rush cost to line. This translate is automatic, and the second step we verify 118 function in the 5 months, and the mark we using to AI can help this the proof. Yeah. The first step we translate the root code to line. Yeah. And this here we see that the root code. Yeah. And this here we see that this in the spec in the line. So spec theorem right in the line. This means here is we see that the condition. The theorem here says that we don't need everything condition, but by the zero function we get it the sum boundaries, and this here the equation. Yeah. Okay. But how can prove it's a theorem? We using the line to check that this theorem is true or false. This check that is varies quickly by some statistics. Yeah. And here is the example. If this means we have the 2 points in elliptic curves, and how can the check that is the 2 points plus? Yeah. Okay. The proof in here we using the AI. Humans write the spec, and the AI have to write the proofs, and we using some techniques. We see that it's okay. Thank you.
Thank you. Let's see if any question. We have. Yeah.
Find new design of new networks. or new algorithms. So looking for
Yeah.
minimizers.
For example, in here is I using this AI to find the new networks. Yeah, and this proof, this is some proof in here we can find this. Yeah. Yeah. New network is.
So this is formal proofs, right?
Yeah.
How about in analysis, you do some estimate. So mostly inequalities, right?
Yeah.
So is it also okay to?
Yes.
Yes?
You see this. You see this project by Tentao. He is
Turnstile?
yeah, Tentao. He
Ah.
is a proof in this here. Okay, maybe. Yeah, is Tentao. He apply
equation
his
theory.
equation
Okay.
theory. Yeah,
All right.
of this. And
Okay. Yeah.
he write is analysis 1 and the analysis 2. Now every the theorem in the books of him is verification. Yeah.
Okay. All right. Thank you. If no more questions, let's thank the speaker again. So we have a tea break, right?
Yes.
Are we? Yeah. Okay. So let's take a break for how long?
30 minutes.
10 minutes. Okay.
30 minutes.
30 minutes. Okay. Half hour. Okay. So let's take a break.
Now it's time for coffee break. Please come back in 30 minutes.
does progress in science and technology come from? From insights gained through practices, from sparks of discovery, from inspiration sparked by the clash of ideas, from elevation achieved through the fusion of different perspectives. In 1654, Pascal and Fermat opened the door to probability theory in their discussion on the problem of points. In 1687, Halley persuaded the hesitant Newton to write his great work, Mathematical Principles of Natural Philosophy. In 1736, Euler attempted to solve the puzzle of the 7 bridges of Königsberg, which led to the creation of graph theory. In the early 20th century, Einstein and Bohr collaborated and completed to develop the theories of general relativity and quantum mechanics, respectively. In 1936, Turing began to explore the universal Turing machine while studying computable numbers. In 1945, von Neumann, who joined the Manhattan Project, introduced the 3 laws to the computer field. In 1948, Shannon proposed information entropy and Shannon's theorem after discussion with von Neumann. In the early 20th century, Fields proved the Riemann-Roch theorem and dedicated himself to global mathematical communication. In 1941, Hedy Lamarr and George Antheil invented a frequency modulation technology, which was implemented in wireless communication systems. In 1965, Gordon Moore summarized practical experience and proposed Moore's Law, which has since been widely followed. In 2000, Gao Kun spearheaded the development of the world's first 1 kilometer long optical fiber network. In 1986, Geoffrey Hinton applied backpropagation to deep learning. Scientific research and technological advancement progress incrementally in this way. Link up theory with practice and aggregate resources. Make active exploration and innovation. Discuss and exchange ideas to ignite inspiration. Develop talent and the ecosystem. Chas Park website. Aggregating global high-value scientific and academic information. Offering multiple intelligent and efficient services. Connecting global academic, technical, and talent resources. Connectivity, innovation, inspiration, fusion. Chas Park website, together with you, driving global scientific and technological progress. Where does progress in science and technology come from? From insights gained through practices, from sparks of discovery, from inspiration sparked by the clash of ideas, from elevation achieved through the fusion of different perspectives. In 1654, Pascal and Fermat opened the door to probability theory in their discussion on the problem of points. In 1687, Halley persuaded the hesitant Newton to write his great work, Mathematical Principles of Natural Philosophy. In 1736, Euler attempted to solve the puzzle of the 7 bridges of Königsberg, which led to the creation of graph theory. In the early 20th century, Einstein and Bohr collaborated and completed to develop the theories of general relativity and quantum mechanics, respectively. In 1936, Turing began to explore the universal Turing machine while studying computable numbers. In 1945, von Neumann, who joined the Manhattan Project, introduced the three laws to the computer field. In 1948, Shannon proposed information entropy and Shannon's theorem after discussion with von Neumann. In the early 20th century, Fields proved the Riemann-Roch theorem and dedicated himself to global mathematical communication. In 1941, Hedy Lamarr and George Antheil invented a frequency modulation technology, which was implemented in wireless communication systems. In 1965, Gordon Moore summarized practical experience and proposed Moore's Law, which has since been widely followed. In 2000, Gao Kun spearheaded the development of the world's first 1 kilometer long optical fiber network. In 1986, Geoffrey Hinton applied backpropagation to deep learning. Scientific research and technological advancement progress incrementally in this way. Link up theory with practice and aggregate resources. Make active exploration and innovation. Discuss and exchange ideas to ignite inspiration. Develop talent and the ecosystem. Chas Park website. Aggregating global high-value scientific and academic information. Offering multiple intelligent and efficient services. Connecting global academic, technical, and talent resources. Connectivity, innovation, inspiration, fusion. Chas Park website, together with you, driving global scientific and technological progress. Where does progress in science and technology come from? From insights gained through practices. From sparks of discovery. From inspiration sparked by the clash of ideas. From elevation achieved through the fusion of different perspectives. In 1654, Pascal and Fermat opened the door to probability theory in their discussion on the problem of points. In 1687, Halley persuaded the hesitant Newton to write his great work, Mathematical Principles of Natural Philosophy. In 1736, Euler attempted to solve the puzzle of the 7 bridges of Königsberg, which led to the creation of graph theory. In the early 20th century, Einstein and Bohr collaborated and completed to develop the theories of general relativity and quantum mechanics, respectively. In 1936, Turing began to explore the universal Turing machine while studying computable numbers. In 1945, von Neumann, who joined the Manhattan Project, introduced the 3 laws to the computer field. In 1948, Shannon proposed information entropy and Shannon's theorem after discussion with von Neumann. In the early 20th century, Fields proved the Riemann-Roch theorem and dedicated himself to global mathematical communication. In 1941, Hedy Lamarr and George Antheil invented a frequency modulation technology, which was implemented in wireless communication systems. In 1965, Gordon Moore summarized practical experience and proposed Moore's Law, which has since been widely followed. In 2000, Gao Kun spearheaded the development of the world's first 1 kilometer long optical fiber network. In 1986, Geoffrey Hinton applied backpropagation to deep learning. Scientific research and technological advancement progress incrementally in this way. Link up theory with practice and aggregate resources. Make active exploration and innovation. Discuss and exchange ideas to ignite inspiration. Develop talent and the ecosystem. Chas Park website. Aggregating global high-value scientific and academic information. Offering multiple intelligent and efficient services. Connecting global academic, technical, and talent resources. Connectivity, innovation, inspiration, fusion. Chas Park website, together with you, driving global scientific and technological progress. Where does progress in science and technology come from? From insights gained through practices. From sparks of discovery. From inspiration sparked by the clash of ideas. From elevation achieved through the fusion of different perspectives. In 1654, Pascal and Fermat opened the door to probability theory in their discussion on the problem of points. In 1687, Halley persuaded the hesitant Newton to write his great work, Mathematical Principles of Natural Philosophy. In 1736, Euler attempted to solve the puzzle of the 7 bridges of Königsberg, which led to the creation of graph theory. In the early 20th century, Einstein and Bohr collaborated and completed to develop the theories of general relativity and quantum mechanics, respectively. In 1936, Turing began to explore the universal Turing machine while studying computable numbers. In 1945, von Neumann, who joined the Manhattan Project, introduced the 3 laws to the computer field. In 1948, Shannon proposed information entropy and Shannon's theorem after discussion with von Neumann. In the early 20th century, Fields proved the Riemann-Roch theorem and dedicated himself to global mathematical communication. In 1941, Hedy Lamarr and George Amthel invented a frequency modulation technology, which was implemented in wireless communication systems. In 1965, Gordon Moore summarized practical experience and proposed Moore's Law, which has since been widely followed. In 2000, Gao Kun spearheaded the development of the world's first 1 kilometer long optical fiber network. In 1986, Geoffrey Hinton applied backpropagation to deep learning. Scientific research and technological advancement progress incrementally in this way. Link up theory with practice and aggregate resources. Make active exploration and innovation. Discuss and exchange ideas to ignite inspiration. develop talent, and the ecosystem. Chaz Park website. Aggregating global high-value scientific and academic information. Offering multiple intelligent and efficient services. Connecting global academic, technical, and talent resources. Connectivity, innovation, inspiration, fusion. Chaz Park website, together with you, driving global scientific and technological progress. Where does progress in science and technology come from? From insights gained through practices. From sparks of discovery. From inspiration sparked by the clash of ideas. From elevation achieved through the fusion of different perspectives. In 1654, Pascal and Fermat opened the door to probability theory in their discussion on the problem of points. In 1687, Halley persuaded the hesitant Newton to write his great work, Mathematical Principles of Natural Philosophy. In 1736, Euler attempted to solve the puzzle of the 7 bridges of Königsberg, which led to the creation of graph theory. In the early 20th century, Einstein and Bohr collaborated and completed to develop the theories of general relativity and quantum mechanics, respectively. In 1936, Turing began to explore the universal Turing machine while studying computable numbers. In 1945, von Neumann, who joined the Manhattan Project, introduced the 3 laws to the computer field. In 1948, Shannon proposed information entropy and Shannon's theorem after discussion with von Neumann. In the early 20th century, Fields proved the Riemann-Roch theorem and dedicated himself to global mathematical communication. In 1941, Hedy Lamarr and George Amthel invented a frequency modulation technology, which was implemented in wireless communication systems. In 1965, Gordon Moore summarized practical experience and proposed Moore's Law, which has since been widely followed. In 2000, Gao Kun spearheaded the development of the world's first 1 kilometer long optical fiber network. In 1986, Geoffrey Hinton applied backpropagation to deep learning. Scientific research and technological advancement progress incrementally in this way. Link up theory with practice and aggregate resources. Make active exploration and innovation. Discuss and exchange ideas to ignite inspiration. Develop talent and the ecosystem. Chaz Park website. Aggregating global high-value scientific and academic information. Offering multiple intelligent and efficient services. Connecting global academic, technical, and talent resources. Connectivity, innovation, inspiration, fusion. Chaz Park website, together with you, driving global scientific and technological progress. Where does progress in science and technology come from? From insights gained through practices. From sparks of discovery, from inspiration sparked by the clash of ideas, from elevation achieved through the fusion of different perspectives. In 1654, Pascal and Fermat opened the door to probability theory in their discussion on the problem of points. In 1687, Halley persuaded the hesitant Newton to write his great work, Mathematical Principles of Natural Philosophy. In 1736, Euler attempted to solve the puzzle of the 7 bridges of Königsberg, which led to the creation of graph theory. In the early 20th century, Einstein and Bohr collaborated and completed to develop the theories of general relativity and quantum mechanics, respectively. In 1936, Turing began to explore the universal Turing machine while studying computable numbers. In 1945, von Neumann, who joined the Manhattan Project, introduced the 3 laws to the computer field. In 1948, Shannon proposed information entropy and Shannon's theorem after discussion with von Neumann. In the early 20th century, Fields proved the Riemann-Roch theorem and dedicated himself to global mathematical communication. In 1941, Hedy Lamarr and George Amthel invented a frequency modulation technology, which was implemented in wireless communication systems. In 1965, Gordon Moore summarized practical experience and proposed Moore's Law, which has since been widely followed. In 2000, Gao Kun spearheaded the development of the world's first 1-kilometer long optical fiber network. In 1986, Geoffrey Hinton applied backpropagation to deep learning. Scientific research and technological advancement progress incrementally in this way.
There is a gentle reminder that our sessions will resume shortly. Please return to the venue.
Okay, so welcome back to the second session. This is emergence of structure in mathematics and learning. Okay, it's my honor to introduce the first speaker, Professor Gergi Ambrose. Okay, Professor Ambrose is a professor at the University of Seger. Okay, he got his PhD from University of College London, and he was a postdoc at MSRI, EPFL at Lausanne, and University Paul Saint-Pierre in Toulouse. Okay, he's the recipient of several national and international grants and awards, including Golden Ring of President of Hungary. Okay, today he's going to talk about the large signed sums, polarization problems, and projection constants of convex bodies. Okay, let's welcome.
Thank you very much for the introduction, and also for the organizers for this wonderful meeting that is very friendly, and I'm sure that all of us are enjoying it a lot. And today I'm a pure mathematician, I'm a classical mathematician, but I would like to talk about three problems in classical mathematics which have connections to computers and AI, and which might help AI, and AI might help us. So that is the theme. So I start with a puzzle. Do you know who this guy is? Oh yeah, Professor Duan is very good. This is not such a well-known image of him, but if we switch forward like 60 years, then this is more familiar. This is Paul Erdős, the most famous Hungarian mathematician. And we are Hungarians, we write the names as in China, we write first the family name and then second the first name. So it's called Erdős Pál in Hungarian, Paul Erdős. And he was really the doyen of Hungarian mathematics and combinatorics. And actually his work is very influential in all of combinatorics, and it has a lot of relations to computer science and AI. So Paul Erdős had a lot of work with different types of mathematicians, all topics, all areas. He was not a professional in every field, but he had friends in every field, and that was this cooperation that made him so productive. And his insight on mathematics has really put light on topics that became central topics afterwards. So he had a lot of collaborations, and then this is a nice image of a collaboration with a young kid. Do you know who the kid is? Terence Tao, exactly. Very good. I should have brought chocolates. So this is Terry Tao. Actually, they are doing work here, but they never had a paper together, so they never had a joint paper. So Terry Tao really started to do mathematical research by the time Erdős died in 96, but this is one of the Hungarian-Chinese collaborations. And another Hungarian-Chinese collaboration, actually a Hungarian-US-Chinese collaboration, is on the next picture. This is Erdős with his friend Ron Graham and Fan Chung, the wife of Ron Graham. And then they wrote many papers together. So this is we should remember that this was during the 1980s, 1970s, 1990s, when there was the Iron Curtain. So traveling was not so easy for Hungarians. But Erdős was really traveling all across the globe, and then he maintained his international net and collaborations. So we are just continuing this tradition of really working together. So he wrote more than 1,500 publications, and then by now he has more than 120,000 citations on them. And well, he solved many problems, but perhaps he is more famous because he posed many problems, many insightful problems that have been open ever since. So Thomas Bloom started a compilation of the Erdős problems. You can find the website erdősproblems.com. And on that, right now, I checked yesterday, there are more than 1,200 problems listed. And roughly 40% of these are solved, but roughly 60% are unsolved. So the Erdős problems, they are really prestigious, and then they mean a constant motivation for mathematicians and also for AI. And now in the age of AI, we have a number of Erdős problems which are getting solved, as we heard yesterday in the talk of Sergey. So let me show you a paper that was published nearly 3 months ago, in which they ran AI to check the Erdős problems, or check a number of Erdős problems. And actually they found out that 9 problems that are published on that website have already been solved in the literature. Actually, it was a very interesting case that one of the Erdős problems was solved even before Erdős posed it. So it was in another paper that Erdős was not familiar with. And then it remained unsolved for it was believed to be unsolved for 50 years. And after that, AI really found out that, this problem has been solved. But really the most interesting case is the first 4 ones. So 2 problems were completely solved and 2 problems were partially solved by AI. And these are really new mathematical proofs. So not like, just finding some results in the references, but new mathematical proofs. So I believe that the list of unsolved problems is going to decrease rapidly in the coming years. And the Erdős problems, they also mean a very good, exercise sheet for AI. Yeah? We will know that AI is really advancing a lot if the number of unsolved Erdős problems goes down by a lot. So I will now tell you about one Erdős problem that we managed to solve, and that is the Erdős-Moser conjecture, or Erdős-Moser problem, that was originally posed in the 1950s by the Moser brothers. And here we are taking a set in the plane, and there is a rule on the set, namely that it should be measurable, so it has some density. And we want to have a set that avoids unit distances. Now, what does it mean? It means that if I take any 2 points in the set, they cannot have distance exactly 1. They can have distances less than 1, they can have distances more than 1, I don't care, but they cannot have distances exactly 1. In other words, if you have, for example, a needle of length 1 and you drop it in the plane, then it is impossible that both endpoints of the needle are in this set. And the question, how much portion of the plane can you select with that property? So how much can be the density of that set at most? And the conjecture says that this density is strictly less than 1/4, so strictly less than 0.25. Now, how can we construct such a set? So if we take the densest circle packing, so the hexagonal pattern circle packing, and let's take circles of diameter 1. And let's now take open circles, so I do not have a problem within one circle, and now just drop out every second circle. In the pattern, so really every 4th circle in them, so 1/4 of the circles are remaining. Then we see that there is no unit distance in the set. So imagine that now these are circles, because within one circle I have the diameter strictly less than 1, and between any adjacent pair of circles I have the distance is strictly larger than 1, so there is no problem. There's no unit distances there. And now it turns out that we can improve that construction a bit, and it was done by Croft in the 1960s. So instead of circles, we move them a little bit closer. We move them a little bit closer so that the density increases, but then we have to be careful with the adjacent pairs, because then if we move this circle a bit closer to that one, then there will be, of course, pairs of points which have distance 1. But we can fix that defect by adding some barriers. So basically, we take the intersection of a circle and a hexagon, and therefore we get these shapes which are called tortoises. So it is called the Croft's tortoise. And then you can run an optimization on how big these like cutoffs should be and what the density is. And it turns out that the optimal density is something like 0.23. And so we know that 23% of the plane can be filled by such a set. Question, can it be improved? And the conjecture is that actually no. So this is believed to be the best construction, but I am 99.9% sure that this will never be proved. So this is a very hard optimization problem. And then, so the conjecture of Erdős was that this density is not more than 0.25. So there is a gap. There is a substantial gap between the best lower bound and then the conjecture. And then, so we managed to prove 2 years ago that the density is at most 0.247, which is strictly less than 0.25. Now, this is not the optimal number. This could be, and this can be improved. I will explain you a bit later. But it definitely proved the conjecture that has been open for like 60 years, and then the bounds were going down and down and down, but they were really converging to 0.25. So there was a belief that maybe the conjecture is not true after all, but then it turned out that the combination of methods and then the use of computers, as I will explain, really helped to break this barrier. And this is the Quanta magazine's cover page, and it's a nice image on that one. With the Croft construction, patterns on a skirt of a lady. So this got some publicity, this result. So how can we do such a proof, or how can we do that estimate? And so the proof combines different things, but eventually it boils down to a linear optimization problem. And that is one thing that computers are very good at. And so this is just the problem that I put there. But what we have to, or what is important for us, is that these constraints are essentially coming from a graph. And the graph vertices, distances, and the congruent subsets of vertices, they lead to linear constraints. And here, this last constraint is coming from congruent subsets. So these graphs are unit distance graphs, which means that we take a set of points in the plane, and then we define an edge to be between any 2 points at distance exactly 1. And any graph will lead to a linear program. And then the question, can we find a graph which leads to the right linear program, or leads to a linear program whose solution is strictly less than 0.25? So this is in a nutshell. And so how these graphs emerge? So let's just see a very simple example. I have a simple graph consisting of only 2 points at distance 1. And suppose that this dark blue set is a set that avoids unit distances. Now it means that if I take this graph and I translate my whole set with the edge vector between the two vertices, then the two translated copies of this set must be disjoint. Because if there was an intersection point, then it would mean that there is a unit distance in the set originally. And therefore, because these two copies are disjoint, we have that the density of them cannot be larger than 1/2. But actually we can go a step further. So what if we don't take just 2 points, but we take 3 points in a regular triangle, an equilateral triangle of edge length 1, and we do the same thing. So we take our original set and then we translate it with one edge vector of the graph, and then we translate it with the other edge vector of the graph. Well, then we see that these 3 copies must be disjoint, and therefore the density cannot be more than 1/3. Now, can we improve on that? Well, if we take 4 points, then it is not possible to take 4 points in the plane so that the distance between a pair of them is exactly 1. But we can still do something. So if we take this graph, which is called the Moser spindle, it has 7 vertices. And if you spend 1 minute of thinking, then you can really see that no matter how we select 3 vertices of this graph, there's always going to be an edge between them. So once again, so these are points in the plane, and then we have an edge between 2 points if and only if the distance of these points is 1. This is what is called the unit distance graph. So the independence ratio of this Moser spindle is 2/7, and it gives us the density estimate 2/7, which is better than 1/3. So these are very simple graph estimates. But then as we improve the graphs, we grow the graphs and make them larger and larger, we have more and more constraints. And then the most interesting constraints are coming from congruent subsets of the vertices. And then you have to apply harmonic analysis and then other methods. But eventually, your search boils down to searching of a graph that has, well, a structure with many, many congruent subsets of the vertices, many, many unit distances, and therefore it generates a linear program that has a lot of constraints. So now this graph that is on the image here, it has 23 vertices, but among these 23 vertices, we have 27 distinct distances, so relatively few distinct distances, and because of that, we have a large number of congruent subsets here. Actually, there's nearly 6,000 congruences, which means that in this linear program, we will have 6,000 constraints, and that gives us a strong constraint on the optimal solution of the linear program. Now, the hard part of this proof was, well, first was the theoretical background, so like really figuring out the whole structure of the proof. But after that, once we had it, we had to look for a graph. And so for this particular graph, writing up the linear program is easy. But the hard part was to find the right graph, and we had to run a beam search in the Moser lattice, which is called, so basically it is the set of points generated by the Moser spindle. But then the search itself, that took 1 week back then. Now it is probably faster. And of course, if you improve the graphs, you add more and more and more vertices, you can push this bound down. So this is an example of an Erdős conjecture which was solved by the heavy use of computers, even though it doesn't count as an AI solution, as Sergey yesterday said, but still, computers helped us a lot. So that is one sort of collaboration between pure math and AI. And now let's go to the other side. So now let's see two problems, or two types of problems, which have applications in machine learning or AI or computer science. So first is the signed sum problem. And then for that, let's just look at the vector retrieval and clustering methods. So suppose that we have a large number of vectors, large number of data vectors, and then somehow I want to do a vector retrieval. So I'm given a vector and I want to find the closest one, which is in this given set. So how can we do it efficiently? And then one way is to do clustering. So what is clustering? So we divide our given vectors into clusters. These are colorful things here. And then first we determine, given a query, we first determine the center of the cluster which is closest to it, and then we just have to run the search within that cluster, so that's a much smaller size. So the question that raises, or one question that raises here, how do we determine the shape of the clusters? And if we would like to use a norm, because that's the natural thing that we do with vectors, so which norm should we use in order to determine the cluster? So we can, for example, say that the clusters are unit ball or translated copies of a unit ball of a norm. And then, depending on the norm, we will have some efficiency of the clusters. So how can we measure the clusters? Well, we basically want to have the average or the worst case errors as small as possible. And then eventually it boils down to, well, one theoretical model boils down to the question that can be formulated as this. So let K be the shape of the cluster. So K is the unit ball of this norm. Now K is just a convex body in RD. It doesn't have to be symmetric, so the norm is actually a Minkowski norm. And then this is the problem that we are asking. So given any vectors in this unit ball, these are representing the errors of the original data values to the centroid of this cluster, or the center of this cluster. I want to have that the sort of average error, which is just the signed sum of these vectors. So epsilon, sigma epsilon I vi, where the epsilons are plus ones are minus ones. I want that the worst case error is small. So the maximum of these is small. And now, well, what does it mean? It's small. Well, I'm measuring the same norm as the norm is coming from or defining the shape of the clusters. And then, well, so we have this optimization, this min-max problem. So we have vectors in the boundary of K, and then we have these epsilon i's, which are signs, and we want to measure the norm of this signed sum in this norm. And question, what sort of bounds can we give on that one? And actually, it turns out that this is again a classical question. So this was the first instance, it was asked by Dworecki more than 60 years ago. And so his question was the following. So suppose that we are given a norm, and suppose that we are fixing a number n. And, well, can we give a bound? Well, first of all, a bound that depends on k and n, so that no matter how we are given n vectors in this unit ball, so v1 up to vn, we can partition it into two parts so that the sum in these two parts is relatively close to each other. And now that is exactly the same as saying, well, that vectors in one set receive sign 1, the others receive sign -1, and then the difference between these two is just this signed sum of these vectors. It is exactly the same. So minimizing this quantity is basically finding a good balancing of the vectors. And so that was the question of Dworecki. And then the very surprising answer that turns out is that the best quantity or the best bound that you find is independent on the number of vectors. So it only depends on the dimension and really only depends on the unit ball of the norm, but it is independent of n. So if you see there is no n in this formula, there is only d here. And so the order of magnitude in d is for LP balls, it is square root of d, and then for general unit balls, it is linear in d. And actually here, the square root of d is optimal, and here the linear d is also optimal. So for example, if you just take the simplex to be k, then you get a linear relation. But once again, so the striking fact here is that no matter how many vectors you have, no matter how large your data set is, you can always find a good balancing so that the signed sum is small in terms of the dimension, independently of the number of vectors. So now we are sort of facing the dual problem. So we would like to, well, give a lower bound on the worst case. So we would like to prove that no matter which norm we take, there is always a bad signing. So there is always a bad scenario. And therefore, we have to switch the min and the max. So before we had the max and min, and now we have minimum and maximum. So basically, the question is this: we are given a vector, or we are given a unit ball k, and then we are given n vectors. And then what is the worst case that corresponds to these n vectors? And so this is what we call the large signed sum. And actually it is relatively hard to calculate the k norm of sums. And this problem turns out to be equivalent to another problem which is much easier to solve, and this is what we call a polarization problem, or a polarization constant, where instead of taking the norm of a sum, you have to take inner products, which are easy to calculate, and then you sum these inner products. Now, the original vectors are on the boundary of your unit ball, and your v vector is in the polar of k. So, but here really the message is that this is much easier to solve and compute than this original k norm formulation. And it turns out that, the two problems are equivalent to each other. So this is what is here. So the two quantities are really the same. So instead of calculating the norm of a sum, you can calculate the sum of inner products, which is much better to do. And the nice thing here is that, well, there's a stability for these quantities and so on. I don't have time for, so I don't go over that. But the nice thing that turns out here is that we can determine the exact minimizer. And it turns out that the exact minimum is attained for the cubes. So in that respect, so the maximum norm, so in that respect, the best cluster shape that you can use, or that you should use, is the maximum norm, the unit ball of the maximum norm, namely the cube. So if in that respect you want to have a good clustering and as good as possible, then you should have clusters of shape a cube. So, and it turns out that cubes are asymptotically better than the Euclidean unit balls that we are usually using. And actually they are winning by a constant of square root of d over the unit balls. So the cubes turn out to be the best, and then the unit balls, they turn out to be, well, essentially the worst, really. Here is it, yeah. Okay, so I don't have time to go over the details here. It turns out that this problem is again related to something which is a classical problem in Banach spaces and functional analysis, and it was studied by Polish mathematicians a lot in the 1970s and 1980s. These are called the one absolutely summing constants and then projection constants. Okay, and so let me switch to the third problem. And the third problem is again coming from, well, the applications are coming from in the 1970s, really. So assume the following scenario. We have a factory, and we want to produce goods in the factory. And in the factory, we have n machines. And I know that in order to produce one good, it needs some time on the first machine, then it proceeds to the second machine, then it proceeds to the third machine, and so on. It proceeds to the nth machine. And let's suppose that the times that are spent at the machines are v1, v2, up to vd. And by normalization, I can suppose that these are at most 1. All right, so, and then this is the process. So I've produced the first machine. It proceeds linearly over the factory. Then I produce the second good. Then I produce the third good, and so on. And my task is to produce all these goods, all these products. And I want to minimize the time. So what does it mean that I want to minimize the time? Well, so if I see one machine where there is a congestion, namely one machine where you know the goods are piling up because that takes too much time, then it is bad because that holds back the production of everything. And then in terms of pure mathematical terms, really the problem that you are facing is that if you are given these, well, n vectors, which are really just coding you the production times of your products, the different products and products. Now basically you want that every partial sum is as close to the, well, k times the average as possible. And now close is meant by the infinity norm. And then the pure mathematical question is this. So suppose that we have n vectors, and, well, after renormalization, we can assume that they sum to 1. Can you order the vectors so that any partial sum has small norm in the infinite norm? And this is exactly the same problem as this factory efficiency problem. And actually, this is also a question that is more than 100 years old. It came up by Steinitz and Levy in connection with the convergence of series. And this is a striking fact here, too, that the best bound does not depend on the number of vectors. So there is a constant that depends only on the dimension and the unit ball, so that no matter how we are given n vectors, we can always, which sum to 0, we can always rearrange them so that any partial sum has small norm. And then, well, so this constant is linear in D, and then there is a strong conjecture that for the Euclidean case and for the L-infinite case, that is for the applications, these are the most important cases. We actually have order of square root of the bounds, but we do not have that conjecture. So here is a picture. So this is what is going on. So we have a lot of vectors. We know that they sum to 1. So if I just put them one after the other, I form this polygonal path. It gets back to the origin. And then it is possible to rearrange the vectors so that they do not leave, the partial sums do not leave, well, a circle of some radius or a sphere of some radius in higher dimensions. And then we know that this radius can always be taken to the dimension, and it can, well, according to the conjecture, it can be taken to square root of the dimension for the Euclidean and for the maximum norms. And this conjecture has been open for 80 or really 90 years. And it's a very famous question, and it has, or it would have, very strong applications as well. And so many of the bad examples come from the facts when we have vectors whose norms are different. And our result basically says that it is enough to study cases where all the vectors have norm 1 or essentially 1. So this is the theorem that we proved, that here is the important part, that you can assume that all the vectors have norm between 1 minus epsilon and 1. So essentially we have unit vectors. And then if we have a bound for unit vectors, then it gives us a bound on the general problem, and therefore it gives us a bound on this flow shop problem that we study. So now this is a very strong reduction. We don't know if this helps or not, but maybe AI will know. And so we are awaiting the solution of this conjecture. And thank you very much for the attention. Thank you.
Okay. Thank you for a very nice talk. Any question? Okay, so yeah, always, yeah, Jinqiao.
This Kakaya conjecture has been proved and is been listed for a candidate for Fields Medal. How about out of this 1,000 problems, any problems solution has led to Fields Medal?
Well, about the distribution of primes, so
related.
But I related to that one, yeah. So not the exact problem, but Erdős had a lot of number theory problems that are about the distribution of primes and then the existence of arbitrary arithmetic sequences, and then this was an important part for the Fields Medal of Tau. So. Yeah.
Maybe Nobel Prize winners, you have 2 in Hungary.
Yeah.
Have they solved?
Yeah, for sure. Lovász solved many Erdős problems. Yeah. Okay. And he has, I don't know, at least 50 papers with Erdős.
Okay.
And also Szemery, the other Nobel Prize winner. So his Nobel Prize was awarded mainly for his regularity lemma. And the regularity lemma came up in connection with work with Erdős. Yeah.
I see.
So in that respect, he was very influential.
Right, yes. Thank you.
All right, thank you again. Okay, so the next speaker is Professor Gao Ting from Huazhong University of Science and Technology. Professor Gao received her PhD from Illinois Institute of Technology, and he worked as a senior machine learning engineer at Twitter. Solved the technical challenges related to model robustness, accuracy, and data selection bias in various data products. Okay. Her current research focuses on data-driven effective dynamics prediction, Schrödinger bridge, optimal control of a non-Gaussian stochastic dynamic system. Okay. And today, her talk is on how mathematical structure rise from uncertainties, dynamics, geometry, and topology.
Thank you so much. Okay. Thank you so much, Professor Wang. Slides? Okay. Okay. So first, let me give my great gratitude to the organizer and the organization team of this great opportunity to give the talk over here. So my topic is related to the session's name. It's called How Mathematical Structure Emerge. Oh, there should be a new version, but this is old one. Rises from uncertainties. So I will outline my talk in mainly these 5 sections. The first one is let's start from the motivation part. So most of us have been familiar with the tipping and critical transitions, which has been happening in a lot of real-world applications. So this kind of tipping is rapid and irreversible. And usually, though sometimes they may be rare events, but usually they get big impact. So people like to create early warning indicators or some spatial temporal biomarkers in different application areas. For example, if it can be seen in climate change or some weather forecasting, as well as the collapse of ecosystem. And in some metastable states, in a lot of applications in biophysics or biochemistry, for example, like the conformational transition pathways of the alpha-D dipeptide is also important to design some drugs. And also the progression of some brain diseases, as nowadays, people are more focusing on this AI agent stuffs, and a lot of hallucinations may come up. So all these problems can be formulated in a mathematical way, what we call the tipping. There are different types of tipping, mainly can be divided into three types, though sometimes we aggregate the R tipping and the P tipping into both the rate-induced one. Nowadays, our team is focusing on noise-induced transitions, which is also more focusing on Levy-induced noise. Oh, sorry. Sorry, this is the old version. I think I have a new version. Someone can get into another slide. So this is not the right version I sent you. Can I send you another one?
Sorry, we are refresh the PowerPoint.
Okay, thank you. Sorry about that. Okay. Oh, thank you so much. So I will move on a little bit fast so we can catch up with the time. So what we want to do is to predict the tipping from real data, because a lot of models nowadays in biophysics are still using the synthetic data instead of the real one. So in real data, there are mainly two types of data we can handle with. One is the time series data with fixed time interval, which is very often to be seen. Another type is the point clouds or probability density snapshots that can be observed on very sparse observation time steps. But sometimes the time interval can even be non-fixed. So the second one is more realistic. Therefore, we want to develop a good framework for handling this kind of problem. And this problem can be solved in 3 steps. The first step is to learn some stochastic dynamical systems from the training data. And then the second one is to define some robust early warning indicators or spatial temporal biomarkers in either state probability or topological spaces. And the third one is to predict new data using some of the indicators we defined before. Therefore, let's go into the step one. Because we are handling the non-Gaussian noise, therefore there's a lot of challenges we have to face. The first challenging is how to design good algorithms, or efficient algorithms, to calculate the non-Gaussian distribution because it's related to some non-local operator or partial differential equations. Then the second challenge is to develop the effective dynamic representations of the dynamical systems, which can be also called the mathematical structures inside of our dynamical systems, as Professor Zima and a lot of professors has talked about these days. Therefore, in a recent publication we have just published last month, we also mentioned in real data applications such as the digital brain, what we call the AI surrogate brain, we also need to pay a lot of attention on the uniqueness, stability, and generalization of our algorithms, no matter it is AI stuffs. But how to do this is to introduce mathematics and the physical laws into our biophysical models, and together with the data-driven problems, we can better to solve this kind of real-world applications. And then if we solve the first step, we can move on to the second one. The second step can be divided into these three different types, which can help us to investigate the tipping phenomena in state probability space or the topological space. So I will go through these kind of different papers. The first one is the state space. So in state space, we mainly focusing on large deviation theory, where a specific action functional called Ansagmo-Halop action functional. It can be used to study the most probable transition pathways, where the probability defined on this tube is what our goal is. And the small z over here is a reference pathway. If we want to solve the most probable pathway, it means we have to maximize this probability, which is equivalent to solve this Ansagmo-Halop action functional in a minimization way. Therefore, this rate function has different forms. Specifically in non-Gaussian case, which is a recent work by Professor Chao Ying in Xi'an Jiaotong University and Professor Duan, who give out this kind of quantitative representation of the Ansagmo-Halop action functional in Levy noise. But when we come into the computational part, the biggest challenge coming from the computational cost driven by this non-Gaussian noise. And unlike the Gaussian case, which can be solved by the calculus of variations, this kind of non-Gaussian formulation makes things hard to solve because we cannot usually get the explicit version of the Euler ranging equation. Therefore, we have to reformulate this problem into optimal control one so that we can solve this problem more easily. For example, if we are given some EEG data, which is high-dimensional time series, we can first project this kind of high-dimensional data onto a low-dimensional manifold. And on this manifold, we can learn whatever we want with different structures of the drift and the diffusion terms. And once we solve these unknown functions by some neural network approximation, we can get a new representation of our dynamical system. And after this, we can also solve some score function, which is quite familiar by these generative modeling researchers these days. So right now we can investigate our functional, which is also our indicator. One is called the Ansagmo-Halop action functional, and the other is the score function. So we did a lot of experiments on some training data. For example, this left-hand side is from our local hospital, and we can learn the data to get the dynamical system and use the OM and the score function indicators to detect the emergence of the onset of some epilepsy patients. After this, we can also use the model we trained based on this local hospital patients, and predict the new public data, which also has some online, which also we investigate some online epileptic patients. And we can see actually the OM indicator is a little bit stable and actually more accurate than the skull function. But because both of them are actually still not that smooth, so it's hard to see, right? So one of the best way is maybe to get some theoretical estimation, but theoretical estimation can only be obtained by the synthetic data. Therefore, we move on to the Levy noise, because once we plug this data and fit them into different distributions, we will find that actually this high-dimensional patients' EEG data can obey the heavy tail distribution, and actually it obeys the super diffusion with the alpha ranging from 1.3 to meaning 1.7. Therefore, to model this kind of data into a new version with the stochastic dynamical system and the Levy noise, then we can see that our indicators based on the skull function and the entropy production rate is much more stable and smooth. But we can also investigate some perturbation theory to prove the theoretical correlation between the two. So this is some illustrated examples that we want to give us heuristic explanations on the distinguish between the Levy noise and the Gaussian noise-driven model. The second part is in the probability space, how do we introduce the tipping, or how do we introduce the bifurcation in probability density manifold? The very easier way to think is previously, if we extend the Zargamon-Holop action functional to be in probability space, it will be the Markov bridge. And then to expand it, it will be actually the Schrödinger bridge, which is like given the initial distribution and the terminal one, we want to find the optimal geodesic between the two. There are many different equivalent forms and the computational algorithm to solve this kind of problem. The most the usual way is this kind of four different types, but I will skip it. One important thing we want to mention is in optimal transport. If the target set is, let's see how to, I will point it. If the target set is non-convex or non-connected, then this optimal transport will not be continuous anymore. So from the Alexandrov theorem in 1950, it can be proved that this kind of optimal transport or optimal plan can be approximated by the linear piecewise functions. Therefore, to obtain the singular sets of the initial distribution is pretty important here. And we want to investigate the dynamics of these singular sets along time. So from here, we actually define our bifurcation in probability space, which is where and when that is splitting happened during the data evolution. So based on some algorithm, I won't go into details, but we investigate Alzheimer's diseases at different stages. And we project this data into low-dimensional manifold and investigate the optimal transport. One interesting finding is we calculate this kind of moving average or rate of the total accumulated energy, which can be also related to some entropy production rate. And we can find that the biggest change of this data evolution dynamics happens when the entropy rate go into the peak, which means when the entropy rate go into peak time, then it is the most probable areas that this point clouds going to be split. So that's the intrinsic mechanism we find our splitting time and splitting points. Another way to investigate the bifurcation in probability space is based on the Jacobi field approach. Actually, this happened when we investigate some curves in the manifold and do the perturbation of it and check the Jacobi field to see the stability of this curve. And when we generalize this curve into probability density evolution, we can also prove that the evolutionary density actually can be the Jacobi field of the evolutionary density can also be obtained in an explicit form in this theorem we have proved. But the condition is that we have to assume that our optimal transport is in a more generalized way. It's not need to be the linear interpolation as the usual optimal transport, but more optimal or more generalized one where the alpha, beta, and the gamma can all be nonlinear. So we tried this algorithm on different types of synthetic data and check whether we can find any indicators that indicates the position and the time where the split happens along time. When we calculate the Jacobi field, the eigenvalues or spectrum can be also easily obtained. We can find that distribution shifts over time of this spectrum. So those subsets of the spectrum where some subsets of the spectrum go from negative value to go from negative value to positive value can give us some indicates on the splitting place and splitting time. So we calculate all these indicators based on this spectrum of the Jacobi field. For example, one interesting example might be this one that we can see actually it got 2 peaks because when splitting, first these point clouds get get a hole inside in the middle set, and then after some time, the boundary also be splitted. So we also check a very interesting example in our recent hallucination data, where we check the question-answer pairs with question with right answer and question with hallucinated answer. We can see that different pairs of different cases can have different ways of evolution, and so their indicators pattern is quite different. So we use these learned pathways or learned evolution densities to predict the hallucination and get much better prediction results than the cutting edge algorithms. For some of the algorithms, it's actually using very complex neural networks such as transformer or attention, but in our case, we only use 2-layer MLP. So our model is quite simple. So I think this is because we find the most important features on this transition. And the third part is the topological one, because previously we can see that sometimes the scale in our density is pretty important. So if we want to learn more details of the scale, we have to investigate and introduce more metrics. So there is a method called topological optimal transport, which can include 3 types of distortions. The first metric is a Euler geometric distortion using the Gromov-Wasserstein distance. And then we also add in the topological distortion, which means as the filtration goes with the persistence homology, we can get for each of the point cloud when it formulates some loops or some rings. In our persistence diagram, you will see a point over here. So this point position will give us information on the birth and the death of our loops. As the filtration goes on, we can get a lot of persistence diagrams. And in these diagrams, we can also compare the width and distance. Where is the topological distortion come from? And then the third part is a hypergraph. Because once we have the first one and the second one, we can do we can check whether the data is on some loops or not on some loops, so that we can create the matrix omega xy over here. So at each entrance of this kind of matrix, the matrix will be binary, which means the point is on the hyperlink or not on the hyperlink. So in this way, we actually can create some hypergraphs. So these three metrics can give us the information on macroscopic, and mesoscopic information from the evolution of the data point clouds. So after we add all these three types of metrics in and do a optimization algorithm, given the initial point clouds distribution and the terminal point clouds distribution, we will find the optimal pathway, but in optimal geodesic, but in a very abstract space. That space is what we call the topological, mirror topological network space. But in this space, if we want to directly study the bifurcation, it will be impossible, because whenever you project the any geodesic in the abstract space into the hypergraph space, the geodesic in the original space will not be conserved in the projected space, which means you will never get the true geodesic in your hypergraph space. Therefore, we have to develop new algorithms to construct the true geodesic of our new hypergraph space. So we propose this approach. First, after we do the initial topological optimal transport spatial coupling, we get the geodesic in the abstract or mirror topological network space. And then we project that into the geometric space. Then in the geometric space, you can just work on with the linear interpolation of your optimal transport, because it still preserves the interpolation property of the optimal transport. And then during the recovered dynamics in the middle, in each of the timestamp, we create the topological structure, which is the same way when we do the persistence diagram. And then after that, we compare each data and the loop, so that we can have our newly constructed hypergraph. In this way, we can construct the true geodesic of our hypergraph space. And after this, we can define our indicators. Right now, our indicators can be easily seen. One is the topological distortion, and one is the hypergraph distortion, and the other is the geometric distortion. Besides this kind of distortions, we can also investigate some indicators from the entropy. Therefore, we define the classical hypergraph channel entropy and the macroscopic version of the persistence entropy, as well as some dual perspectives, for example, like the hypergraph entropy with different version of the vertex version or the edge version. We can also prove some error bound, which I will skip. So for example, if we have this training data, which is depicted by this 4 red box data. So we only use these 4 snapshots. We want to predict the left 96 snapshots, because totally we have 100 timestamps. So how to use these four snapshots to get the whole dynamics of the picture is through our above algorithm we have mentioned. So in the following is the dynamic we have recovered based on our algorithm. We can also compare with the synthetic data based on different indicators. Above ones are distortions, and the middle, these ones are the hypergraph entropy and the persistence entropy. So they are all consistent with each other in different cases. Even sometimes the macroscopic version, like the topological distortion, will work. Sometimes the topological distortion is not sensitive, but the geometric distortion works. Sometimes all the distortion is not going to be well because there is some noise inside the ring generation and the distinction. Therefore, at that time, we can check the entropy also works. So there are different indicators based on different scales. And we also check some real data from the stroke patients. So the first initial part is the 3 months patients. The terminal one is 1 year's stroke image. And we want to investigate, are there any specific regions of the brain that have most change or bad changes, or even the shrinkage of the brain area, brain volume. So we also check different data with our indicators. I think this is a good try that we can do more real data to it. So the conclusion is that we develop an algorithm to investigate the true geodesic of the hypergraph space, so that we can try different versions of the indicators on. And so to conclude, we have developed 3 types of indicators from different perspectives. But in the future, we think the nonlocal Waterston geometry will be a promising areas, as well as the second-order dynamics of the nonlocal geodesics. So that's all for today. Thank you so much.
Thank you, Professor Gao, for a very nice talk. Okay, any question? Yeah. Right.
Could you explain the part in a bit more detail? So do you have any tail distribution, I suppose? This is why you use a leading noise.
Mm-hmm.
Then did I understand correctly? You use the entropy production as a warning criteria, or?
It's a, so for the Levy, actually, because the data has intrinsically should be intrinsically modeled as the Levy noise instead of the Brownian motion one. So what we want to prove is that the indicators defined by Levy score instead of the Brownian's score function is much better. In this way. But the theoretical proof, what we are still working on, is through some perturbation theory, so that we can get the intrinsic or mathematical guarantees of what's the specific difference between the Brownian case and the Gaussian case. Yeah, hopefully we can discuss with you in the near future after we formulate this one.
Okay.
Yeah.
Thank you very much.
Thank you very much.
Any other question? Yeah. Yes.
Yes, thanks for the very nice talk. So, as far as I understood, so it seems that you add some extra terms into your loss function and train the networks. Yes. So I'm not sure if this extra terms can include much of the computation cost or not, yeah, in your computation.
Oh, in that Levy case, actually, we did a small trick that the input of the input is still spatial and temporal, but the output is the whole integral of the Levy part. So it's not that cost, yeah. but yeah, but just approximation. So as Professor Zimmer said, we should have some theoretical guarantees. Yeah.
Sure. Okay, thank you. Yeah.
Okay, let's thank Professor Gao again.
Thank you, Professor Wang.
Okay, so our last speaker is Professor Owens Patrician, okay, from St. Petersburg University. Is the speaker here? Oh, okay, sorry about that. Yeah, okay. So Professor Patrician is ex-director of AI Center of St. Petersburg State University, which in 2024 becomes one of the biggest AI center in Russia. Okay, he's a professor of mathematics modeling of energetic system. Okay, of St. Petersburg State University. Okay, today he's gonna talk about kernel binary optimizer, latent-free optimizer for binary neural networks. Okay, please. Okay, let's welcome. Yeah.
Thank you very much, dear colleagues. Well, actually, the title of the talk is not what I wanted to present in the program, and some of the points are the information is not updated yet. But anyway. So today I wanted to present a algorithm for the binary neural network training. And the previous title of the talk was also about the algorithm for the binary neural network training, but yeah, so let's. So the two algorithms, which one of I will present and the other one was in the program, they were a part of the project which already finished a few years ago with the Huawei. And the papers are submitted to ICML. I'm not sure if they are will published or will not published, but one way or another, one day or another, they will be published. Anyway, so I will be presenting this algorithm, and this one I will skip for the future. So my talk will be, I think, slightly different from the other talks. I think most of the talks are more mathematical, more mathematical or more related to physics. My talk will be somewhere more inclined to machine learning and training algorithms. So I will try to go faster with this part. So the binary neural networks, why they are important? So the key idea of the binary neural network is that some part of the neurons are binary. It means the values are -1 or +1. So usually in practice and I think in some of the presentations today and yesterday, the neural networks had weights with 8 FP or 16 FP. So each weight costs maybe 8 or 16 bit and so on. But in the binary neural networks, most of the weights, maybe 80% of the weights are binary. So this means you can reduce a lot the computational time for the inference and also computational time for the training. So this is very important cutting edge direction for the edge devices. Yes. Yeah, but there is a problem. There is a problem that you need to know how to train it, right? Because if we consider the neural network and stochastic gradient in the continuous space, then we can build sufficient theoretical results, convergence guarantees, and so on. But for the binary case, there is a problem. Yes, for the binary case, there is a problem. So for the binary neural network training, there are basically two general methods. One is called PQT, and the other one is QAT. So the QAT is quantization-aware training, And a PQT is post-training quantization. Post-training quantization is a pure engineering way, like when we consider a similar version of the binary neural network, but with float point neural network, like continuous space weights, we train it and then we do the quantizations. Very similar, simple thing, like engineering, pure engineering approach. But more mathematical approach is quantization-aware training. There are many methods. The idea is that when we are doing the training, we should use the approximation of the sine function and use it to compute the gradient, and then we hope we can get a neural, finally we can have a binary weights or partially binary weights in our neural network. So the problem of the binary neural network training is that each weight, or most of the weights, are -1 or 1. So it means we use a kind of sine function. So we should understand, yeah, the sine function. So the problem of the gradient is that the gradient is hard to compute if we have a sine function. Yes. Okay. So we have considered in our research a series of baseline algorithms, and that's very interesting to mention that most of these algorithms are published not in the mathematical journals or mathematical conference, but most of them are published in AI conference, and especially in a computer vision conferences. One paper is published in NIPS in the end of 2024, but related to more Bayesian variational inferences. Not very practical, but still exist. But it's important to mention. It is important to mention that all of these kind of top baseline algorithms that have good results on the practical benchmarks, they are not pure optimization algorithms. So here you can see that most of these algorithms change the neural network architecture itself. So they mostly work with the neural network architecture change rather than on the training. And this is at the same time is advantage and disadvantage. Disadvantage from mathematical point of view, from the optimization theory. Advantage from the AI point of view, yes, but from optimization theory is not very important. I will skip the detailed description of this part. Maybe it's not very interesting for you. Yeah, but I will just briefly introduce the IRNet algorithm, because this is a kind of important. I think it's most mathematical from these algorithms. So the idea of the IRNet algorithm is that they use the approximation of the sine function, which has the following shape, yes. And the idea is that during the training, with the learning rate change, they change the approximation. So they make the approximation of the sine function closer to the real sine function as the learning rate change. So in the beginning of the training, the approximation of sine function is pretty bad, I would say. And at the end of the training, the approximation of the sine function is pretty good. Yes? Why they have this idea? Why they have this idea is that because in the beginning of the training, you want to allow a gradient map, because they use the gradient. Yeah, that's very important. Actually, they can use Adam. Yeah, but they use theoretically stochastic gradient. They need to allow ways to change a lot. Yes, in the beginning. In the end, you can see that in these places, if we use this approximation, then the coefficient in the gradient will, from this approximation, will make the gradient values very high. So actually, that's you can imagine that, right? This will mean that the convergence will be very fast. So it can kind of stuck to the same place where it belongs. So that's why in the beginning the approximation is not very precise, but in the end very, very precise. Yes. This is just a comparison of the on the benchmark the existing methods, and usually in practice. In practice, people use for the benchmarking classification problem and super resolution task. That's not very important, I think, from theoretical point of view. So I wanted to directly go to the algorithm which I present today. So the idea is we modify the EarNet version, so the most mathematical kind of the algorithm for binary neural networks training in the following way. So we use the idea of the oscillations. Oscillation is when during so it is important to mention that we work in the space of the continuous weights. Yes, so we use anyway the Adam or stochastic gradient descent to change the coordinates of the weights, and we can compute the loss function of the neural network. Just on each step of the training, we use sine function and we compute the loss on forward and so on. But we still move in the continuous space of the weights. Yes, and but what we do is we compute the oscillation parameter. Oscillation is in the there are several research papers for the binary neural network training, and they purely empirically study the oscillation. Oscillation means that during the training, the binary weights change. Yes? So let me show you. Yeah, so this is just an example for a specific neural network architectures. The binary weights change. So from optimization point of view, changing of the weights during training, that's a good thing, right? That's a good sign. But in a practical binary neural network part, most of the weights are binary, but the other part is continuous. So, but we need to use the same continuous optimizer to optimize all of the weights at the same time. So, so in the beginning, maybe we are happy about the binary weights change, but in the end of the training, if the binary weights change a lot, then the continuous weights will be harder to converge. So, and actually this is one of the ideas also about the EarNets when they change the approximation of the sine function. So the idea of the algorithm is that we take into account the oscillation parameter in the approximation of the sine function, and the approximation of the sine function is included, of course, in the gradient computation. Yes, and then this gradient is used to do the training. Yeah, so the idea is pretty simple. Also, we have a specific adaptive learning rate update, which adds some dependency also on the oscillation parameter, but mathematically speaking, this is not very interesting point. Yes, the most interesting point is the dependency on the oscillations. Yeah, this is I already presented. So of course, since the practically I will show the results on the benchmark. So this algorithm works. It's better than the baseline algorithms and so on. But of course, we are interested to prove that it converges. Yes, so one thing is converges, and the second thing, maybe we can build a convergence rate. Yes, so. Under specific assumptions, under some specific assumptions for the accuracy or the closeness of our approximation to the sine function, we can, maybe you cannot see it directly, but so we can prove the proposition that the gradient the gradient, the binary, we call it the binary gradient, the gradient which is computed in the points of the binary weights, is similar to the gradient of alpha. Yes, And then for the case of the binary, when the loss is convex, when the binary loss is convex, binary loss is the loss function, the loss function of the initial neural network, which is continuous in the points of the binary points, or binary weights. Yes, so we can prove that the algorithm converges to the optimal weights. Yeah, but the proof is I would say new, because for the binary neural network training algorithms, this kind of proof was not obtained. Yes, the assumptions are pretty standard for the gradient like methods, but there is one important thing. Yes, so the standard kind of the algorithm for the binary neural network training, or very classical one, is called STE. Is also use approximation of the sine function. Also, so for this kind of algorithm, we also can prove the convergency. Yes, but in practice, STE kind of algorithm converges faster than our algorithm, and actually any other algorithm. So so that's why we had to prove that even the STE converges faster, but it converges to the worse result. But this is a small result, maybe not very important at this point in this presentation. So the second thing is we wanted to show the convergence rate. The convergence rate we provide, of course, for a specific mathematical model of the neural network, so for a specific type of the neural network, which is based on the one hidden layer and the ReLU activation function. Of course, we can build two hidden layer and the n hidden layer, and yeah, but the idea was that we wanted to derive the convergence rate. And it's also interesting that this convergence rate also, for the first time, the convergence rate was obtained for the case when the weights are binary. Yeah, so usually convergence rate obtained when the weights are continuous, but this is convergence rate are binary. And these are just the results on the benchmarking. So ablation experiments. I'm not sure if this is very interesting for the audience, but the idea is that on the standard benchmarks for the binary neural network training, like super resolution neural network and classification problem, we have shown that all of the innovations and modifications of our algorithm, like the approximation of the sine function, the activation function approximation, and our learning rate, they are really all influence the final result. But this is like the numerical result maybe. And also we show that our algorithm outperformed the existing baselines on the super resolution neural network architecture. So this kind of the benchmarking is pretty a standard for the binary neural network research direction, I would say. Yes. So here we show that if we apply our algorithm to any of the neural network architecture modifications, it will improve the final score. Also, we show that we can improve the GPT kind of training. Yes, this is a new result for the binary neural networks. So usually they are tested on the computer vision tasks. Maybe because computer vision is very interesting for for tiny devices computation. So we also do the training of the GPT tool, and we also show that we can obtain some performance improvement. And yeah, I think this is it. Yes. Thank you very much.
Thank you for the very nice talk. Okay, let's see if there are any questions. So your binary. So each neuron in your neural network, all the neurons are binary,
Yeah.
or it's only the end the last layer?
Yeah. Thank you for a question. So, actually depends on the architecture of the neural network. So, because in a binary neural network research direction, they are standard like SOTA architectures. But usually most of the weights, maybe 80 or 90% are binary, and the others are 4-bit, 8-bit, and so on. There also are emerging neural network architectures for the large language models, but they use some mixed precision. But I think it's more engineering kind of results.
So your problem, it doesn't have to be binary itself, right? For example, I can understand the decision problem, okay, either 1 or 2. I mean, either -1 or 1. But many of the applications are not like that, right?
Yes, of course.
So it has.
Yeah, for example, the super resolution task is a pure not binary problem. But the idea is just how to compute inside the neural network. Just the computation need to have a binary weights.
Okay.
Yeah, so we have the continuous weights inside the neural network, of course. So finally we have the continuous output, like a probability prediction of probability of a class.
Yeah.
And so on. Yes.
Okay. Yeah.
Yeah, there's one student has a question. Chen Wenjie, okay.
Thanks for very good talk, and I'm wondering, can we introduce the value of 0 into the elements of the weight and the bias of the neural network, and the loss will not be so big change?
Can you please repeat the question? I cannot hear.
Your talk is about the binary neural network, and can we introduce one more value, 0, into the value of the weight and the bias of the neural network?
It's a good question. I think theoretically it is possible, but practically in engineering there's this kind of neural networks are not even maybe they exist, but they are not used. Yeah. So the purpose of our work was to build the efficient training algorithm, and so that it will be theoretically supported. Yeah. So theoretically justified. It means we do not change the neural network architecture. We just consider the classical binary neural networks.
Okay, because I think if you introduce value 0 into the neural network, the structure will be sparse and can use in the very maybe high dimensional problems or something like that.
Yeah, I think so. Yeah.
Okay.
Yeah.
Thank you.
Okay, if there's no more question, let's thank speaker again.
Thank you very much. Thank you.
So I guess this is the end of the morning session. Right? Let's thank all the speakers in this morning. These 2 sessions. Okay, so that's lunch.
As we come to the end.
Oh, okay.
Thank you. As we come to the end of the forum, let us take a moment to look back at the past 2 days' discussions. We wish that the video carries the touching memories of the forum. Thank you, all the guests. Now we will move to the closing speech of the forum. Please welcome Professor Duan Jinqiao.
Okay. Hello, everybody. This is a remarkable day and a half. I really enjoyed the presentations myself. I will recall a few moments. For example, we mentioned that 2023, the spring of AI, and I also heard that Herbert A. Simon, Nobel Prize in Economics, and bachelor's degree in political science in Chicago. He spent most of his career at the Illinois Institute of Technology, where I worked until I came to China. So he was a remarkable person and made a significant contribution in the early stage of what we have been talking about in this forum. We also heard about other newer, younger generation of AI researchers. So this, you see this we have touched a number of fields in science, mathematics, physics, and computer science, or informatics, and applications in engineering and in science and medical sciences and so forth. So I hope the spirit from the Kopernik Forum and the Chess Park will continue, and I hope you will remember this forum in the city of Shenzhen in southern China. We hope to see you again. So long. Auf Wiedersehen. Goodbye.
Thank you. This brings us to the end of the forum. Thank you all your participation. We look forward to the future academic communication. And now we warmly invite you to join the lunch at Curtis Restaurant at first floor. See you there and enjoy your lunch.